Welcome to The Explainer. Today, we're going to tackle a foundational and, let's be honest, a really satisfying technique in calculus, separating the variables to solve differential equations.
But before we even get into the how, let's talk about the why. Why should you care? Well, it turns out differential equations are basically the language of change. They're the hidden math behind everything from weather forecasts and stock market trends to how planets move. They're everywhere.
So what is one of these things really? At its heart, it's super simple. It's just any equation that has a derivative in it. Something like dy over dx. It's basically a rule that connects a function to how fast it's changing at any moment. And that, right there, is an incredibly powerful idea.
Okay, so here's our game plan. We'll start with the technique itself, then see it in action with some textbook examples. After that, we'll get our hands dirty with some practice exercises, tackle some real exam-level problems, and finally, we'll clear up the super important difference between general and particular solutions.
All right, let's dive right in. The very first method we learned for solving these things is awesome because it's so direct. It's really all about getting everything nice and organized.
And the entire goal, the whole principle, can be summed up in two words: isolate and conquer. Your mission, should you choose to accept it, is to get all the y stuff, including the dy, on one side of the equal sign and all the x stuff with the dx on the other.
All we're doing is a bit of clever algebra to get the equation looking just like this. See, a function of y is hanging out with dy, and a function of x is with dx. Once you've managed to do that, and believe me, you can, the hardest part is already over. Seriously.
And this right here, this is our playbook. It's a simple four-step process we're going to use every single time. First, you separate. Then you integrate. You got to add that crucial constant of integration, the plus c. And finally, you solve. That's it. 4 steps.
Now, let's put that theory into practice. We'll walk through a couple of official textbook examples just to see how this method works in the wild.
Okay, here's our first problem, fresh from the textbook. We need to solve dy over dx equals 1 plus x divided by 2y. And they gave us a starting point, an initial condition. Y is 3 when x is 0.
Okay, let's follow the steps. Step 1, separate. We'll multiply by 2y and dx to get the y's on the left and the x's on the right. Now, step 2, integrate both sides. The integral of 2y becomes y squared. The integral of 1 plus x becomes x plus x squared over 2, and don't forget the plus c. Now, for the final step, we use those values they gave us. We plug in y equals 3 and x equals 0, and that just neatly tells us that our constant c has to be 9. Done.
Now, this next example might look a little more intimidating, but don't let the algebra psych you out. The process, it's exactly the same. We're still just isolating the y terms and the x terms, integrating both sides, and that gets us to the general solution you see here. The core technique never changes.
All right, theory is one thing, but practice is where it really clicks. Let's work through a few problems from exercise 10a to really lock this method down. Okay, now this one is interesting. We've got dy by dx equals e to the power of x minus y. And the little trick here, before we can separate anything, is we have to remember our old friend, the laws of indices.
So we rewrite e to the x minus y as e to the x times e to the minus y. See, now it's easy to separate. We bring e to the y over to the left side, integrate, and we get e to the y equals e to the x plus c. Now we just use our initial condition, y of 0 equals the natural log of 2, and that tells us our constant c is exactly 1. And with that, we've got our final answer.
This next question tries to be a little sneaky. It tells us the gradient of a curve is 5xy cubed. But gradient is just a fancy word for dy dx. So it's the exact same kind of problem, just dressed up in different words.
So we set up our equation and we separate. That gives us y to the minus 3 dy on one side and 5x dx on the other. We integrate, we simplify a bit, and then we plug in the point 1, 1 to hunt down that constant of integration. After a little bit of algebraic cleanup, we get our final expression for y squared.
All right, I think we've got the technique down. So now let's apply this to the kind of stuff you might actually see when the pressure's on in an exam.
Here is a classic exam question. It looks so simple, but it is incredibly important. dy over dx equals 3y. This is the fundamental equation for all exponential growth. whether you're talking about bacteria in a lab or money in a bank account. So, we separate the variables, which gives us 1 over y dy equals 3 dx. Integrating that gives us the natural log of y on the left and 3x plus c on the right. Now, to get y all by itself, we have to get rid of that natural log. And how do we do that? We use its opposite. We make both sides the exponent for the number e. We exponentiate. That gives us y equals e to the power of that whole thing, 3x plus c. And using our index laws one last time, that simplifies really nicely into y equals some new constant. Let's just call it k times e to the 3x.
Okay, so this brings us to a really crucial point. What does that plus c or that k actually mean? This is the difference between having one single answer and having a whole universe of possible answers.
So when we solve an equation and we still have that plus c hanging around, what we found is the general solution. It's not one single curve, it's an entire family of curves that all follow the same rule. It's only when we're given an initial condition, a specific point that we know is on the curve, that we can pin down that constant and find the one single particular solution.
And this quote here from an expert just nails it. The general solution is your starting point with that flexible constant. But the boundary conditions, that's just a fancy term for those starting values they give you, those are the keys that unlock the one specific particular solution out of that whole family.
We've just mastered a really powerful and direct method for solving a huge class of differential equations. But it does lead to a much bigger and more interesting question. What do you do when an equation just can't be neatly separated like this? What comes next?